Alright, let's get started with the exam solution. In this problem there are 6 stations. 1, 2, 3, 4, 5 and 6. The processing times are 44, 40, 55, 60, 50 and 40 seconds per razor. So that's why the capacity is given that there is only one worker in each station. 1 over 44, 1 over 40, 1 over 55, 1 over 60, 1 over 50 and 1 over 40. Given that this is the lowest capacity, D is the bottleneck. So what is the process capacity? Well, the process capacity is given by the bottleneck's capacity. That's why it is 1 over 60 razors per second. But remember, we want the answer in terms of razors per hour. So we need to find the conversion factor. Going from razors per second to razor per hour, well, we know we can get rid of seconds by multiplying by second on the top and minute on the bottom. 60 seconds equals to 1 minute. And we can get rid of minute by multiplying minute on the top and hour on the bottom. So the relationship is 60 minutes equals to 1 hour. So we can get rid of second and second, minute and minute. So we have 1 over 60 times 60 times 60. Then we get the answer in terms of 60 razors per hour. Okay, the next question is, what is the direct labor cost associated with producing one razor in terms of dollars? Well, we know that we pay $25 for each worker, and there are 6 workers. So for each hour we have to pay $150, right? $150. The flow rate in that time is 60 razors per hour. So we have 150 divided by 60 is $2.5 per razor. Okay, what's the labor utilization? Well, the labor utilization, we know the demand is not a constraint, so the cycle time is 60, right? The cycle time is 60. Given that the cycle time is 60, we know the idle time in the first station is 16, the idle time in the second is 20, idle time in the next is 5, 0, 10 and 20. So we know the total labor content is 289. If you add the labor content and the total idle time, it comes out to be 360. Comes out to be about 80.27%. Okay, let's go to the next question. The next question asks, over the course of several months, you visit this donut shop, and then you observe that the queue length is 10. So that is, you know, the I on average is 10 customers. It takes 3 minutes to get in and get out, so you know T is 3 minutes. Okay, I want to find R, so I equals to R times T. I is 10, R is what I'm after, T is 3. R equals to 10 divided by 3. But remember, this is in terms of customers per minute. On average, 10 by 3 customers arrive. I don't want 10 in terms of minute, I want in terms of 3 hours. So 10 over 3, if we had to convert into hours, that would be 60. We need 3 hours, so 3 divided, this goes away. So it is 600 customers in that 3-hour period. Okay, what are the 3 dimensions of operations? Well, the global footprint, this doesn't make sense. Ethics, we didn't talk about that, so that's not the case. The real competition is between B and C. But if you look closely, B has this efficiency and cost. Remember, in operations, efficiency and cost are the same thing. So C is the answer. All right, the next question, Molly Madison. In this question, what happens is, it takes 62 minutes to bake the bread, and we want to know, we want to have an R of 4,000, so we need to know how big an oven to make. So how big an oven to make sounds like we need I, right? Because that's how much inventory it has to hold at any given time. We want our R to be 4,000 units per hour, right? Breads per hour. And we know our T is 62 minutes. Okay, so I equals to RT. We want R to be 4,000. times T is 62. The problem here is 62 is in terms of minute. You can convert this in terms of hour by dividing it by 60. So it comes out to be 4,133.33. So we need an oven big enough to hold this much breads. Okay, that's how big our oven should be. Okay, our next question is, a manufacturing company had reported a sales of 60 million last year. Remember, this is sales. We need to find the COGS. So COGS is what? And it had an inventory of $20 million. Okay. Now we want to find the inventory turn. So inventory turn equals to COGS divided by inventory, right? But we don't know what COGS is. Okay. But what is the relation we have is whatever we sell for $2,000, it costs us $1,250. Well, something we bought for something that costs us $1,250 is gonna be sold for $2,000. Then something we sold for 60 million, how much must it have cost us? Well, it must have cost us, suppose X, right? Assume X. So X is really, the relation is whatever portion 1250 is of 2000, the same portion is that value, that X value out of 60 million. So this comes out to be about 37.5 million, right? So our COGS is 37.5 million. 37.5 million divided by our inventory is 20 million. Comes out to be about 1.875. That means we turn 1.875 turns per year. We flip our inventory 1.875 times. Okay, that's all we needed for that part of the question. Let's assume the company has a holding cost of 25% per year. And what is the holding cost for a product that was $1,250? Okay, so remember, it is 25%, but we flip the inventory 1.875 times. The cost of the product is $1,250. So we need what we're after, the holding cost per unit of the product is $166.66. Okay, throughput time cannot be reduced in the process. Well, reducing the utilization at the bottleneck obviously would reduce the throughput time, right? Because that just means reducing the time, the processing time at the station. So obviously this is not the answer. Reducing the interruptions. Well, if you reduce the interruptions, it's like reducing the processing time again, right? Changing the sequence on the activities, on the other hand, does not reduce the processing time because you just take. So think about the earlier example we had with the 6 stations. Only by moving the station A in the A after a station. So suppose we have A, B, C, and we move this around, putting the B in front of A does not change a thing. The D is still the bottleneck, right? So that doesn't change the thing. So B is the answer. So that's exactly what you're going to explain here. Reducing the utilization of the bottleneck is same as reducing the processing time at the bottleneck. Reducing the interruptions, if the interruption is being reduced at the bottleneck, well, you reduce the throughput time. The B is the only answer that doesn't make sense. So B is what we're after.